right, so with Lecture 5, we talked about the relative abundance of the elements, or the relative abundance of the isotopes of each element, I should say, and how to calculate the average atomic mass knowing those abundances, or how to calculate the abundance knowing the atomic mass. All right, so now we're going to talk a little bit about the periodic table. We are going to get into the periodic table a lot later. That is to say, we'll be getting into it a lot, and this will happen a little bit later. But right now, what we're going to do is we're going to look at the periodic table and look at the different sections of the periodic table. You notice it has this funky sort of block shape. The reasons for that is what we'll get into later, but for now, let's look at the different groups. The rows of the periodic table, called the periods, the groups are the columns, and the groups are they're groups of elements with similar chemical activity, similar behavior, similar properties. Okay, so the ones you need to know about, that you really need to know about, are first off, on the left-hand side, everything to the left of this diagonal line. And this diagonal line is the metalloids, and to its left you have the metals. This also includes these guys down here. Okay, technically, this long row on the bottom is squeezed in right here. We pull it out and put it underneath so that it just keeps the periodic table from being absurdly long. Also, we mostly don't pay attention to those guys. But over here you have the metals. Most of the elements out there are metals. Okay. So over here to the right of that diagonal line, you have the nonmetals. It's a much smaller group. And then that diagonal line, as I said, is the metalloids, or semi-metals. Okay. But you also have, as I said, the groups, columns. Over here you have the alkali metals. Okay, that's lithium, sodium, potassium, rubidium, cesium, and francium. Then you have the alkaline earth metals, beryllium, magnesium, calcium, strontium, barium, and radium. Okay, so those are the first two columns in the periodic table. Hydrogen, very rarely will it act like a metal. Usually hydrogen's behavior puts it over here, right to the left of helium, and it acts, well, even then it doesn't really act like these guys all that much. They have their own group name, their own set of behaviors. But it acts more like these guys in general on this side, on the right-hand side of the periodic table. Hydrogen can usually count it as a non-metal. But for other reasons that, again, we'll get into later, you can think of it as being over here on the first column, so that's where it's usually put. Okay, so alkali metals, alkaline earth metals, this big block in the middle here, okay, it looks, I don't know what color that is, sort of a dusty rose, I guess. Those are the transition metals, because you're making the transition from this side over to this side, so these are the transition metals. And these over here, a very fancy name, the post-transition metals. I guess they just couldn't come up with a good name for those. These metals down here, as a block, they're sometimes called the rare earth metals, because they're rare, I guess. But they also come under the name of this period, this section of the period is known as the lanthanoids, because they come after lanthanum here, number 57. And these are known as the actinoids, because they come after actinium. Like I said, we mostly don't deal with those, because, well, everything after uranium is actually artificial and man-made, and you don't find it naturally occurring anywhere on Earth. And most of them only exist for like the minuscule fraction of a second inside of, high-powered nuclear reactors. So we don't even, see them really. So that's all the metals. And now coming over to the nonmetals, you have the noble gases, so-called because they're very non-reactive. It's hard to get them to react with anything. In fact, I'm pretty sure neon and helium won't react with anything at all. Argon, you have to beat the ever-loving crap out of it to get it to react with anything. Krypton, you beat the crap out of it, it'll react, and then the products will stick around long enough for you to actually study them. Xenon can form somewhat stable products. Even that is pretty hard to do. Coming right to the left of the noble gases, you have the halogens, fluorine, chlorine, bromine, iodine, astatine. Halogens all share properties. Astatine is radioactive, so we don't usually talk about it. Normally we just talk about these four: fluorine, chlorine, bromine, and iodine. Technically, these groups all have names. The chalcogens for the oxygen group, the pnictogens, I mean, actually it's a silent P, they're just pnictogens for nitrogen. But because you're definitely into weird territory there, they usually don't. When I say weird territory, I mean you have nonmetals, then metalloids, then metal. Nonmetals, metalloids, metal, nonmetal, metalloids, metals. So even though they do share some significant properties, the fact is the properties change pretty radically as you go down those groups. So they don't usually talk about them as groups. Whereas for the halogens and the noble gases, the alkali and the alkaline earth, those do definitely have common properties in that way. The rest of the non-group ones, the transition metals, they don't share similar chemical activity, but they do share certain trends and properties, similar for the post-transition metals, that allows us to sort of consider them all as a sort of group, a pseudo-group, okay, a semi-group, that sort of thing. So those are the various sections of the periodic table you need to know about. Okay? You definitely need to know the names for the alkali, alkaline earth, noble gas, and halogens. You need to know that these are the transition, these are the post-transition metals. You need to know these are the semi-metals. You need to know that everything to the left of the semi-metals, or metalloids, everything to the left of that diagonal line are the metals, everything to the right are the non-metals. So you need to be able to recognize, more or less at a glance, metal versus non-metal. And that's not that hard to do, because there's only 10. This little triangle here are the only non-metals you'll ever really deal with in chemical reactions and chemical compounds. Carbon, phosphorus, selenium, iodine, bromine, chlorine, fluorine, oxygen, sulfur, and nitrogen. 1, 2, 3, 4. 10 total elements in the non-metals. Anything that's not in there, it's either a metal, a semi-metal, or a noble gas. And the noble gases, non-metals, and semi-metals, those are all small enough groups that hopefully you'll get to recognize them with time. I'm not suggesting you memorize all the elements in the periodic table. That would be kind of a silly thing to do. But I suspect that if you do spend long enough working chemistry problems, studying chemistry, that sort of thing, these will become relatively familiar. It's a group of roughly 20 elements, not too hard. And don't forget hydrogen over here. So, now we're going to talk about moles. Okay. The mole is a measurement of quantity. Okay. Mass is a measure of the amount of matter in an object. But the mole is the number of items, sort of. So, this is important because when you look at, say, an atom of hydrogen, it has a single proton, and that's it, giving it an atomic mass of, on average, 1.008. Whereas an atom of oxygen is 8 protons and either 7 or 8 neutrons. And it has an average atomic mass of, I think it's 15.9998. So every atom of hydrogen is much smaller than any given atom of oxygen. And this makes a big difference because when you look at, for example, water, okay, it's going to be always 2 atoms of hydrogen and 1 atom of oxygen. But its mass is going to be roughly, 18.01. Okay. Because 2 atoms of hydrogen, 1 atom of oxygen adds up to about 18.01. So measuring mass it can tell you about the atoms that you're looking at. But for chemical reactions and things like that, you really need some sort of real measurable quantity that tells you about the actual atoms or molecules that you're dealing with. Because in chemical reactions, it's 2 molecules of hydrogen plus 1 molecule of oxygen, making 2 molecules of water. Or you can look at it as, 4 grams of hydrogen plus 32 grams of oxygen, making, 36.02 grams of water, which is not nearly as easy to sort of wrap your head around as the 2 to 1 to 2 sort of relationship that is directly expressed in the chemical reaction. And that is what moles are for. Okay? A mole is a relationship between the number of particles. Remember, a particle is just, a thingy. Okay? So a particle could be an atom of iron, it could be a molecule of hydrogen, or it could be a molecule of methane. It could be any number of things, so long as you can sort of come up with some way of describing the thing you're looking at. In fact, you could talk about, a penny. I should have probably drawn something easier to draw. That's Abe Lincoln. You could talk about a penny as an individual particle, and you could talk about a mole of pennies just as easily as you could talk about a mole of atoms. So, what is a mole? Well, the mole, the concept, I can't remember exactly who derived it. I suspect it was an Italian named Avogadro, because of a thing called Avogadro's number. N sub A equals 6.022 times 10 to the 23rd. Right. So that's Avogadro's number, 6.022 times 10 to the 23rd. And that's 6, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is going to work. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Like I said, it wasn't going to work, but it's a really big number. And what Avogadro's number tells us is the number of, for example, let's look at carbon-12. If you have this many atoms of carbon-12, okay, so, 6.022 times 10 to the 23rd atoms of carbon-12. All right, so that's what's in that box. Then it will have a mass of 12.01 grams. And if you look at your periodic table, you'll see that the average mass of carbon is 12.01 atomic mass units. So that makes me realize I've screwed up. It's not carbon-12, it's just average carbon. If it had been carbon-12, then the mass would be exactly 12 grams. Okay. Similarly, if you have an Avogadro's number, if you have 6.022 of hydrogen atoms, 6.022 times 10 to the 23rd hydrogen atoms, then those hydrogen atoms will have a mass of 1.008 grams, the same as the atomic mass of hydrogen on the periodic table. For oxygen, it would be 15.9998, I think it is. For boron, 10.811 grams. So Avogadro's number just ensures that if you have that many atoms then they will all add up to a mass in grams equal to the mass in atomic mass units of the element. So you see here on the periodic table, 1 mole of hydrogen, 1.008, 1 mole of helium, 4.003, lithium, 6.941. So it's just the mass underneath the elemental symbol on the periodic table. All right, that's been about 15 minutes, so let's go ahead and cut it off here, and we will come back for the rest of this lecture in Lecture 7.